Hello, everyone. Thank you for being here, first of all. I'm going to be talking about our recent work where we try to understand the computational power of bosonic systems from a complexity theoretic perspective. Here is the outline of the talk. I'll start by trying to answer a question that has been asked to me a couple of times already this week, which is why should I care about bosons? After which I'll try to give you a bit of background on bosonic quantum information so that we are all on the same page when we start talking about the main content of the work. After which I'll talk about the computational complexity of bosonic systems, talk about our mean result, the set of results that lead to that mean result, and I'll conclude with giving some final thoughts of um, what this project helped us understand better about bosonic systems. I'll start now. So why should I care about bosons? As you guys all know that one of the main aspects of research in quantum advantage is to develop technologies which can implement these advantageous quantum algorithms for whatever task you want to do it for, right? And in that context, bosonic quantum platforms, so like photonics and superconducting cavities, have become increasingly relevant because of different experimental breakthroughs. This diagram kind of tries to show that for like where it's used in different contexts. But for me, I'll just focus on bosonic quantum computing for now. Um, and in this context, bosonic platforms are relevant because of like experimental breakthroughs such as generation of large scale entanglement in bosonic platforms and error correction capabilities in bosonic platforms uh, being quite remarkable. And in that sense, it's important to learn about bosonic systems because they might be the right platform for bosonic quantum computers. However, the type of computations that they perform are fundamentally different from the ones performed by qubits or qubits. Um, so this is because of the simple fact that formally the computations that are performed by qubits slash qubits are discrete variable quantum computations, whereas the computations performed by bosonic platforms are called continuous variable quantum computations. They are different because whereas for discrete variable quantum computations, operators and states are living in finite dimensional Hilbert spaces. Um, for continuous variable quantum computations, operators and states are living in infinite dimensional Hilbert spaces. Other than that, whereas in discrete variable quantum computations, you have bounded operators with a discrete spectrum. In continuous variable quantum computations, you have operators that are possibly unbounded with possibly continuous spectrum. So, for example, if in discrete variable quantum computations, you are dealing with um, spin and polarization, in continuous variable quantum computations, you are dealing with position and momentum, which are by nature continuous and unbounded. And there have been a bunch of recent results which have proved that this difference in mathematical structure can lead to fundamental differences in quantum information processing. So there was a result by Francesco Anamele and his collaborators last year, which proved that if you are talking about the tomography of bosonic systems, even if you are bounding the energy of such bosonic systems, the complexity of tomography is exponentially greater. This was a talk in TQC last year, if I remember correctly. And then there was this talk by Lucas Brenner and his collaborators, which was about how to factor an integer with 3 oscillators in a qubit. I think it was a couple of days ago, which proves that like if you are using bosonic platforms, you can actually do factoring in constant space as compared to polynomial space when you are using qubits. And then this leads to the natural question that does this difference in mathematical structure also affect the nature and power of bosonic computations as compared to discrete variable quantum computations? Um, and I'll focus on the second part, which is the power of bosonic computations. And so the motivation is somehow twofold. Experimentally, it's because these platforms are becoming relevant and we want to understand them more. And theoretically, it's just this possibility that maybe they are more powerful than even a DV quantum computer. And this kind of motivates this work. So before I move to the work, I'm going to give a brief overview of CV quantum information and a bit of complexity theory. The easiest way to think about bosonic quantum systems are systems which are described by Hamiltonian, which are Hamiltonian of the quantum harmonic oscillator. Of course, there are other bosonic Hamiltonians, but I think this is the most simple one that we normally deal with. Um, and these have certain properties that I have already kind of alluded to. So one of them being they live in infinite dimensional Hilbert spaces, and their operators possess a continuous spectrum. Two commonly seen operators in bosonic Hamiltonians are creation and annihilation operator. And in that context, you can define the coherent states, which are basically the eigenstates of the annihilation operator. They are so-called classical because if you look at the evolution of a coherent state, you can see that the average value of position and momentum in these coherent states mimic the position and momentum of a classical particle in a classical harmonic oscillator. And there is other like computational point of view for calling them classical, which I'll get to in a bit. And finally, I'll talk about the vacuum state at some point. These are just zero boson number states. Uh, so these are kind of one thing that you need to understand the project. The other is the Gaussian and non-Gaussian quantum states. Gaussian states formally are defined as states which have a Gaussian function as their phase space representation. And if you're not familiar with this formalism, you can think of Gaussian state as just the CV analog of Clifford states. On the other hand, Gaussian unitary gates are operations that convert Gaussian states to Gaussian states. Of course, there are more formal ways to define it, but for the context of this talk, that's okay. But we have this result by Mari and Iser from 2012, which proves that circuit that starts with Gaussian state and we only have Gaussian gates throughout, we can classically efficiently simulate them. And this is the analogy with the Clifford operations, that they in themselves do not offer any quantum advantage. So if you need any quantum advantage, you need to inject some magic or the CV analog of magic, non-Gaussianity. So we need like non-Gaussian gates to have quantum advantage. And one such non-Gaussian gate, which is relevant in, for example, cubic phase gate, is in the superconducting platforms, is the cubic phase gate. And why am I introducing these two things? Because after this, I can define the notion of universal bosonic computations, which was a bit unclear until earlier this year, where in a work by Francesco Argiani and his collaborators, they proved that universality in bosonic systems can be defined as the capability to engineer a Hamiltonian polynomial in position and momentum operators. A common retort to this would be, but not all physical Hamiltonians are polynomial and in position and momentum operators. However, they prove that you can approximate even those physical unitaries up to arbitrary precision with Hamiltonian's polynomial in position and momentum operators. And this combined with the result by Lloyd and Bronstein from 1999, which proves that Gaussian unitary gates plus cubic phase gates gives us a natural circuit for universal bosonic computations, which is vacuum state being fed into a circuit with Gaussian unitary gates plus cubic phase gate. After which I'll move a bit into complexity theory. The simplest definition that you can think of complexity theory is it's like a branch of computational science where we are categorizing different physical systems according to the type of problems that they can solve. And as such, it is a natural avenue to compare computational power of two physical systems by simply comparing the complexity classes that they belong to. And in this context, we have the complexity theory of DV quantum computers or qubit-based quantum computers. Which has been well studied for a while now. And the important class that we care about is the BQP, which is the class of problems solvable by a DV quantum computer efficiently. And we have this inclusion that BQP is in PP, PP being the class of problems solvable by a probabilistic classical algorithm with success probability greater than 50%. And there are tighter inclusions for BQP such as P sharp and AWPP, but for the context of this talk, this inclusion suffices the point that I want to make at the end. After which we finally move to the content of the work, which is the computational complexity of bosonic computations. So the complexity theory of bosonic quantum computers was not really developed until last year, where Ulysse Chabot and his collaborators wrote this paper about bosonic quantum computational complexity, and they introduced the class called CVBQP, um, which is the class of problems solvable by a bosonic quantum computer efficiently. And they also include this inclusion, which is that CVBQP is in X space. X space being the class of problems solvable by a classical computer using exponential amount of memory. And this inclusion is kind of unrealistic. And why it is unrealistic? A simple way to think about it is like this inclusion is like saying that any real number is less than infinity, which is true, but that doesn't really tell you much about the nature of the number. Is it like 1 or 1000? So if you want to understand the nature of bosonic computations a bit better, you need a tighter bound on CVBQP, and which is the main result of this paper, that we managed to improve this bound from X space to P space. P space being the class of problems solvable by a classical computer using polynomial amount of memory. And the rest of the the rest of the talk is dedicated to understand this proof a bit better, more intuitively, because the proof is rather technical, but I'm going to go through the various proof steps to make sure things are non-technical but understandable. So first of all, we describe a complete problem. So a complete problem for complexity class is such a problem that if you can solve that problem, you can solve every other problem in that complexity class. For CVBQP, the authors already defined this complete problem, which is you have been given this universal bosonic circuit. You measure the number of bosons in the first mode, and then you decide whether the number of bosons lie in region A or region B with high probability. So these guaranteed that it is going to lie in one or the either with high probability. And these are the type of promise decision problems that you normally deal with in complexity classes. Um, and we want to solve classically simulate this particular architecture or this particular problem and see what the complexity class of solving this is. However, this circuit in itself is too complicated to classically simulate, or there are ways to simplify this circuit. One of them is more logical, and the other argument is a bit technical, where we can prove that if you have a cubic phase gate sandwiched between a Gaussian gate and its Hermitian conjugate, you can replace the Gaussian gate by passive linear unitary gates, but by just modifying the cubicity. Uh, and you have to trust me on this for now that passive linear unitary gates are a bit simpler to simulate than Gaussian unitary gates. The reason will be clear a bit later. And doing this throughout the circuit, we can replace all the Gaussian gates except the last one by passive linear unitary gates. So this is one like circuit simplification that we can do for the complete problem. The other thing that you can do is right now it's a decision problem that you want to decide is it A or B. But you can actually argue that if you can estimate these probability for all n up to high enough precision, then you can logically make the decision yourself. So if you can classically simulate the probability of bosons lying in region A and bosons lying in region B with high precision, then you can just make the decision yourself. So we change it from a decision problem to an estimation problem, and these two arguments combined help us to come up with a problem that we can actually devise a classical algorithm for. And this classical algorithm is based on a fact that the initial vacuum state is a coherent state with alpha is equal to 0. And coherent states have this property that if you input a coherent state into a passive linear unitary gate, what you get out is another another tensor product of coherent states with different coherent state parameters. But this is an analytical description that you can get given the description of the passive linear unitary gates. So that is one simplification that we can do. The problem is there are these cubic phase gates which do not change a coherent state to a coherent state, of course, because they are non-Gaussian. Um, and to get around this problem, we give this lemma, which says that you can approximate the action of a cubic phase gate on a coherent state by writing the output state as a superposition of coherent states. And we prove that this is exponentially close to the actual output state. And the physical reason behind, or the physical intuition behind this is you want to in some way simulate the non-classicality that is brought upon by this cubic phase gate. And one way to do it is you keep the states classical, but you put them in a quantum superposition. So the quantumness somehow comes because of the superposition. We prove that this is exponentially close, and we also prove that the description of such a superposition can be described in parallel polynomial time. Parallel polynomial time basically means that you can get the description in polynomial time, provided you have an exponential amount of processors on your hand. Um, and so this is the first approximation that we do, and kind of the only approximation that we do really. And given this approximation, the algorithm is rather simple, that you are starting with a coherent state. Whenever you are encountering a passive linear unitary gate, you just get the analytical description of the output coherent state. And whenever you are getting a cubic phase gate, you just approximate the output as a superposition of coherent states. And when you see that when you do it over and over in the circuit, at the end, as an input to the final Gaussian gate at the circuit, you get a superposition of coherent states. And this action of Gaussian gate on that is the superposition of Gaussian states. Uh, and this output state is exponentially close to the actual output state of the circuit. And again, this can be described in parallel polynomial time. And once we have this output approximation as a superposition of Gaussian states, the problem of probability estimation of the number of bosons on the superposition of Gaussian states is already a well-posed problem, which is Gaussian boson sampling for those of you who know. And there are ways to like classically simulate Gaussian boson sampling. We we take one particular method which allows us to estimate the probability with exponential precision in parallel polynomial time again. So you now at the end of the algorithm, you see that you can express the output state in parallel polynomial time, and you can do the probability estimation again in parallel polynomial time. So in the end, you are approximating the probability up to exponential precision in a parallel polynomial time. So you are solving the like complete problem in parallel polynomial time. Now, this means that the complete problem lies in a classical complexity class called p-time. P-time is the class of problems which can be solved by a classical computer in polynomial time with an exponential amount of processors. So this is not exactly p-space, right? But there was this result by I think it's Wiley and Anderson. Like there are two different papers from 1978 and 1986 which prove that p-time with polynomial with p-time with the time complexity being polynomial is equal to p-space. And the proof is rather technical, but the simple intuition to understand is that um, if you think of every complexity class as rectangles in an xy plane, with x being the space and y being the time axis, p space is basically a rectangle whose length is polynomial and its width is exponential, and p time is a rectangle whose length is exponential and whose width is polynomial. So you're kind of tilting the rectangle in going from p space to p time, and you can prove that this is this is can be done in such a way that the two classes are equivalent. So we prove that this is in p time, and p time is equal to p space, and we can conclude that the complete problem is in p space. And this gives us the complexity that we require, which is that CVBQP is in p space. And this is a way to represent what the progress was done during during this work, which was we had this initial CVBQP complexity class, which was in exponential space, and through the course of this work, we managed to squeeze it into p space, which was a significant reduction. And this is a more real. This is not most probably not the most optimal bound, but this is a more realistic bound because at least it says that bosonic quantum computer cannot solve everything, which the last inclusion seemed to imply, which was of course incorrect. Um, and this leads us to a couple of thoughts about this result. The first thing is there an exponential advantage in bosonic quantum computers even as compared to discrete variable quantum computers? I know the first retort to this would be that yeah, but maybe you can reduce the complexity classes even further. And I agree that this is a good line of research, but there have been results that I already mentioned, like yeah, the complexity of tomography result and the factoring in constant space results, which can seem to suggest that maybe there is an exponential advantage. And the second most common critique of this would be, okay, but you are never really talking about energy. If you like, the one reason people can theoretically think that bosonic quantum computer is more powerful is simply because you have an infinite dimensional Hilbert space, so you can like access more states, and maybe by accessing more states, you can solve harder problems. Um, but you are never really going to access infinite dimensional Hilbert space in any realistic scenario, just because the energy is finite. And then the question then becomes, even can you have a CVBQP be greater than BQP even when you are bounding the energies to some finite values or realistic values? And this kind of leads to this argument that when we are talking about classical complexity theory, or even like DV complexity theory, you are talking about time and space as resources. We argue that for bosonic complexity theory, you have to have a third axis, which is energy, and the different classes needs to be defined with respect to the energies as well. And yeah, after that, the question becomes, is it still possible to get a quantum advantage? I don't know the answer for now. And finally, one open question from here is that we are taking the cubic phase gate as the non-Gaussian gate, but of course, the cubic phase gate is not the only non-Gaussian gate. You have the Kerr gate as well, and many others. And the question becomes that does the nature of the non-Gaussian gate also affects the nature and power of bosonic computations. Um, and the answer is again, this is an open question, so I don't really know right now. In DV quantum computers, I think it's more or less equivalent no matter the like the gate you take which injects magic. But is it the case in bosonic quantum computations? I don't know. But for now, the aim of this talk is to was to shed a bit more light on the computational power of bosonic computations through the lens of complexity theory, and I think we managed to define a well motivated complexity class, gave a realistic bound on it. There are some open questions, but still it's a like a budding field, so there are bound to be some open questions, but I think these reflections help us understand these systems a bit more. With that, I want to thank my collaborators, the institutes that I am a part of, our team, and you can read our paper here if you want, but right now I'm open to taking questions.
Hi, yeah, thanks for the talk. Yeah, just a question on your expectation on how this diagram might look like in the future. Do you have any guess or expectation on whether or not you could put
I
CVP?
think my intuition says that like if you are not bounding the energy, um, okay, that's not realistic completely, but if you're not bounding the energy, I do like my physical intuition says that maybe CVBQP is more powerful than BQP simply because of the fact that like you can access more states. Um, whether then this advantage becomes realistic when energy is like realistic, I'm not sure. But well, the complexity result even holds even for bounded energy, so there is some sort of hope that this might be the case, but I would like to believe it is the case that it is more powerful just because like I'm working on it, but like I cannot give you a correct answer for now.
Thank you for the nice talk. I had a quick question about the uh, inclusion into p-space.
Yeah.
So if I want to show something like this inclusion is strict, then like, do you know some methods that can prove that some like p-space complete problem is not solvable by CVBQP, or is that like hopeless?
Oh, you would want to say that like it cannot solve every problem in p-space, you mean?
Yeah. So I want to say that there is a problem in p-space that it cannot be solved by CVBQP.
Yeah, I think one way to like reduce the complexity further is to say do what you are doing. But I'm not like aware of a problem which like directly proves it for now. The other way is to just like try to find better simulation algorithms which can do it in PP or P sharp or like being equal to BQP. Maybe just like if you can come up with an algorithm where DV quantum systems just simulate a bosonic quantum system, then you can just say that their complexity classes must be equal. So yeah, that's the one way, and the other way is to just like this is the kind of direction that we are kind of trying to do, which is like we can prove that CVBQP is lower bounded by P space. So like then it's equal because of upper and lower bound. So that's
Oh, so you expect them to be equal?
well, I would like to expect, yeah, why not?
Thank you.